earth science area, NASA is looking at two big questions. The first one is, what is happening with the Earth today? Trying to understand better the processes that are going on throughout the planet. And then with the data that we gather, we're looking at what will happen in the future. The Earth Science program has a fleet of airplanes that they've been flying for many years, and just recently we've added UAVs to the mix of airplanes. UAVs give the ability to go to places on the planet that other airplanes can't reach. We can go to different altitudes, we can go to different ranges. We give the scientists the ability to gather data they have not been able to gather before.
UAVs, short for Unmanned Aerial Vehicles, are playing an important role in helping NASA investigate global ecological events, such as melting polar ice caps and hurricanes. But to do this, instrument systems and communications capabilities needed to be adapted for the reduced payload capacity and limited satellite bandwidth available in UAVs. In 2003, NASA established a university-affiliated research center, or UARC, in partnership with the University of California. Leveraging world-class engineering capabilities from across the University of California system, the UARC began providing support for the Airborne Sensor Facility at NASA's Ames Research Center, which is responsible for developing, managing, and maintaining NASA's airborne remote sensors, including those used in UAVs. One of the early sensors created for use with UAVs was the Autonomous Modular Sensor, or AMS. Created to support NASA's Western States Wildfire mission, AMS was first flown in 2006 on board the Altair, a UAV jointly developed by NASA and General Atomics based on the Predator B platform.
The AMS captures data in 12 color regions across the spectrum. There are essentially 8 channels which take pictures in roughly the region that the human eye can see. There are several other channels that are in the shortwave infrared. After about 1 micron, say about twice as red as the reddest we can see, smoke starts to become transparent. So after about 1 micron, we can see the location of terrain and fire underneath a smoke layer. As we move out farther and farther into the infrared, redder and redder, what differentiates parts of the image is what temperature they are. So we can tell the difference between sun reflecting off targets on the ground, areas that have been recently burned across, and areas which are actively burning. In the Western States Fire mission, AMS was used to take pictures through smoke and lay them on terrain in such a way that we could locate the hot spots in a fire on a map that could be used by the firefighting personnel.
In October 2006, after the successful completion of several significant milestones, the Autonomous Modular Sensor was removed from the Altair and the Western States Fire Mission team stood down. But that changed quickly after a small blaze set by an arsonist grew quickly into the devastating Esperanza wildfire in Southern California. An emergency support request was made by then California Governor Arnold Schwarzenegger to NASA for remote sensing over the fire, and the AMS and Altair were quickly returned to service. The success of the Autonomous Modular Sensor and Altair during its initial flight experiments and the Esperanza fire paved the way for NASA's acquisition of an advanced variant of the Altair, and in November 2006, NASA took delivery of an MQ-9 Predator modified for research use. Dubbed Ikana, from the Native American Choctaw word meaning intelligent, conscious, or aware, this new UAV continued NASA's Western States wildfire mission. During the 2007 fire season, Ikana was able to provide overflights for dozens of fires, including the Zaca fire, one of the largest forest fires in California history.
As we overflew the fires, we collected the imagery. That imagery was then corrected on board for the locations of the fire. In other words, it was aligned properly with the earth and the terrain, the local terrain. That data that was sent down through the satellite link to the fire incident commanders directly so that they could actually see where the fire was on a terrain map in 3 dimensions.
During the blaze, incident commanders were able to use data provided by ICANA and the AMS to better manage firefighting resources, and in one instance, even redeploy firefighters away from a potentially deadly situation. Looking to build upon the success of Altair and ICANA, NASA expanded its airborne science fleet in 2007 with the addition of 2 long-duration, high-flying Global Hawk UAVs. Procured from the Air Force, the Global Hawks arrived with only the avionics required to fly them.
One of the biggest challenges of bringing Global Hawk into the Earth science realm of research was the ability to change payloads out fairly quickly and inexpensively. The Global Hawk aircraft is flown by the Air Force, flies 2 instruments. For the various types of research we were going to be conducting, we knew that we would need to adapt the aircraft to be able to fly as many as 12 instruments. So we did quite a bit of structural mods internal to the aircraft to be able to mount these instruments all over the aircraft, including under the wings. But we also had to route the data and the power systems throughout the aircraft.
We changed the communication system. We put an Ethernet system on board for the instruments to talk to each other instead of everything talking back to the central computer, and a new power control system for the payloads as well, so that we can individually turn off and on specific instruments. There was a great deal of work that went into it.
Working in close collaboration with NASA, engineers at the UARC set about developing a remote sensor network to enable remote mission operations for the Global Hawks. This network would allow the aircraft to be integrated with ground-based systems via satellite uplink in order to provide real-time monitoring and management of science instrument payloads. To do this, engineers needed to create a number of new hardware systems to work with Global Hawk, including an experimenter interface panel to provide power and communications connections to science instruments, the Master Payload Control System, which integrates science instruments with Global Hawk's ground communications systems, the NASA Airborne Science Data Acquisition and Telemetry System, which provides time and location data to science instruments for recording when and where measurements are taken, and a variety of communications protocols and software systems for gathering and visualizing aircraft and science instrument data.
The sensor network is an important step forward for UAVs, in particular because it allows scientists to respond to the data that they're collecting as they are collecting it. In the past, on the ER2, for example, they would have to send their instrument off and hope that it worked. They wouldn't know what kind of data they got until it landed. This allows us to change as the conditions change.
Enabling UAVs for remote sensing Earth science mission requires considerable engineering to develop robust instrument systems that are compact and lightweight, as well as efficient IT infrastructure to use the limited bandwidth provided by satellite communications to manage those instruments. Over the past decade, the UARC has collaborated closely with NASA to develop modern instruments and remote sensor networks to enable ever more advanced Earth science missions.